we will come to the actual semiconductors which we are using. So some of the features of that. So last lectures we were devoting to the basic origin of energy bands and how one can calculate basic calculations of energy band structure of the materials were discussed. And if somebody is interested in going beyond and see do the calculations, I have there is a tool available online, so one can vary the potential, the different kinds of potentials, and study different parameters. One can vary and study the energy bands. So somebody who is interested in going deeper, because band gap engineering is a very important area, especially in nano electronics or nanotechnology. So it will be quite interesting. Those who would like to pursue studies in nanotechnology or nanomaterials, so it will be of some interest. So it is actually the tool is posted. So I mean, we are not going to discuss anything about that tool. So that is, but only thing is those who are interested, they can go to it, go through it, and that is from NanoHub. Have you heard of NanoHub? Hello.
No, sir.
Yeah,
No,
actually,
sir.
NanoHub is a website for education of nano. It's by one US university. So Purdue University. So I don't know how the right pronunciation. You can go to nanohub.org and see that where a lot of resources are available for micro nano materials and technology. So some of the materials which we have discussed, or I have been using the resources from them for the last many years. So in this, in our discussions also, I have used resources from NanoHub. Actually, one resource I very often use. So they have resources, lecture materials, PPTs, then tools, online tools. The advantage is you don't have to. You need only a net connection. You can use the tools. There are various simulation and animations are available about the materials, devices, etc. Even including carbon nanotubes, devices, MOSFET, etc. Many, and a lot of lectures are also available. Then a lot of animations are available, and so that is a quite useful tool. So I've been using it for the last many years. So anyway, some of the so that tool is posted for this calculation of this energy bands using the different potentials. Yeah. Anyway, so before getting into today's discussion, I would like to mention two things. One is I have actually I made a factual mistake, so I want to correct that. Anybody notice that? Did you notice any factual mistake or in my last lecture? Hello.
No, sir.
Actually, I mentioned about one movie about which
Yes, sir.
Yes, sir.
Interstellar. Interstellar.
yeah,
Yes.
actually, I said Inception. That is a different sci-fi movie, which I
Yes,
have,
sir.
even though I have not seen. And Interstellar was the movie I was referring to, where this
Yes, sir.
time dilation. Actually, father is much younger to his daughter, and all those things. So it happens because of the time dilation and all those details are there. So that was the movie I was referring, because I'm like very concerned about this, because as a teacher, we should, as far as possible, we should be factually right. We should not mislead people, mislead students actually. So I wanted, fortunately, immediately after my lecture, my daughter pointed it out to me. I was listening because she was fond of these both the movies. She was trying to show me Inception, which I have never seen. But Interstellar we watched together, so she reminded me. So I got mixed. So instead of Interstellar, I said Inception. So sorry for that. Then second thing is there was some question on the chat which I may not have noticed. So today onwards, if, we will take up the questions. If you have any questions, either you ask straight away or you can put it on the chat box. Small questions. So don't because that will be a distraction for you. Don't type lengthy questions. So, but small clarification or simple question, that is a good thing. So you can post it there. Probably towards the end of the presentation, we can pick up that, or somebody can mention those things. So last lecture, I missed those. But fortunately, I have seen that Prashant has taken care of that and answered nicely. So I think she is satisfied with Prashant's answer, or still some confusion is there. She's there today,
Yes,
Prashant.
sir.
Yeah, she's there.
Yes, sir. I'm there.
Yeah. So that your question is, you are satisfied with the answer.
Yes,
Actually,
sir.
why?
Somehow.
Actually, that is very important. And when you are talking about the system, identical condition means all the conditions should be satisfied. Then only you can talk of identical system. But then you may ask why we have mentioned that, actually, because there is an essential. If you go through the slides about classical and quantum, you can make out the difference. In quantum, the observer can disrupt the system. Actually, the observation itself can disrupt the system, whereas in classical mechanics we don't consider that, actually. So identical condition, because here, even though the conditions are identical in the case of quantum mechanics, the observation itself can interfere with. So that creates problem. That is why that uncertainty principle comes. That is why we have to explicitly mention. Whereas in classical mechanics that doesn't happen. Identical conditions means of course all the variables of interest should be same. So actually you have rightly pointed. So that reminds me of one interaction I had 2 3 days before with a school student. So I was discussing with him about the boiling point, because you did mention that Cochin and Kurukshetra, there are temperature differences will be there. Then there are other parameters also. Can you mention, other than temperature, any other difference? Can you mention between Cochin and Kurukshetra or Delhi? Any other
Yes.
difference?
Air pressure.
Yeah, air pressure. So, for example, let us take the boiling point of water. Will it be same in Cochin and Kurukshetra? Where it will it be same?
No, sir, it will
Boiling
be
point.
different.
Sir, it is
No,
going to vary.
no, no.
So where it will be high, Kurukshetra or Cochin?
Cochin.
Yeah. So actually it depends on the sea level, because Cochin will be at the sea level, zero, and whereas Delhi will be around 200 meters, I think. Mount Everest will be, or Simla will be around 2000, and Mount Everest will be. So in fact, if the so generally the if you if you want to cook something, it will be very difficult in Simla, because you have to use a pressure cooker. If you on the top of the Mount Everest, anyway, the boiling. Can you anybody any idea what will be the boiling point of water at the top of the Mount Everest? Have you heard of this? How much changes take place? Any idea? Actually, it will be around 69, 70. Actually, that is degrees Celsius. The boiling point of water is around that range, 69 to 71. That is the range of the boiling point of water. Uh,
68,
Pardon?
68 kind of.
Yeah, see, between 68 to 71, that range it comes. You can see the difference. See, there around 20, 30 degrees the difference is happening. So we are not when we said that identical conditions means all the conditions are identical, the pressure, temperature, everything. Then only, but in the case of classical quantum mechanics, even if those conditions are same, the observation can disrupt. So that is why we have mentioned explicitly. Otherwise, anybody will think if under identical condition everything will be same. What is the why? What is the fun in mentioning it? Yeah. So anyway, so that was regarding what we have discussed in the last lecture. Any other thing you would like to mention, or any questions? Yeah. Any questions?
Sir, sir,
Yeah.
sir, it is said that light has zero rest mass.
Yeah.
But whenever we saw the theory of the black hole, its gravitational pull is so strong that even
Yeah.
light can't pass through it.
Yeah.
So why gravity is acting upon light when
No,
it has
actually,
no
oh
mass?
yeah, that's a very interesting question. This shows, this is a proof, one proof for Einstein's equation. Energy and matter are same. Photon is a form of energy, but energy also will be influenced by the gravitational pull, even though it doesn't have any rest mass. So matter and energy are interchangeable. So that is proof. In fact, this uh, black body, sorry, the black hole uh, bending of or pulling of light is an evidence for E is equal to mc squared. Actually, but there are other proofs also, because the nuclear emission, where you have seen that the energy released is of the order of E is equal to mc squared, the mass. So it shows that these photons also has some of the features of, even though it doesn't have any rest mass. So that is so energy and matter are one and the same. Actually, they are two. You can't say states, two stages of same thing. Actually, so that way, when under heavy gravitational pull, even the light cannot escape. So that simply shows that matter and energy and one and the same. So does I satisfy you?
Sir, a little bit.
Yeah.
Because I asked this question, the same question to our physics teacher.
Hmm.
They said something like the photons are being absorbed by the matter inside the black hole. That's why those are not reflecting; those are just absorbing
No, it
light.
is not the question of absorption. Actually, you have to understand the difference. See, for the gravitational pull is not an attraction. Sorry, it is not an absorption. So that is, I can straight away say absorption. You cannot use the word absorption there. See, when see, for example, we are pulled by Earth when we are falling body. So that is not an absorption actually. It is some. See, these are some of the fundamental force: gravitational force, Coulomb force. These are fundamental force of the nature actually. So you cannot that explanation is not right anyway. Yeah, it's
Okay,
not
sir.
absorption. Hello.
Yes, sir.
Yeah. So I
Actually,
yeah.
they were saying that the like what matter does is firstly it absorbs the light which reflect on it, which fall on it. Then it reflect it back.
No, no, that explanation is absolutely wrong. You can read yourself or like more about it, but we have to see it in a like it cannot be explained on the basis of that. I can straight away say that explanation is wrong. I don't want to say somebody is wrong, but then wrong is wrong. But that is not the kind of explanation one can look for that. I may not have given you full satisfaction with my answer, but definitely it is. I can say with a lot of confidence that it is not absorption or reflection. It is just like a gravitational pull affects the matter. There is no say what is happening. So same thing is happening with the light also. So that is so there is no distinction between this. See, gravitational pull attacks. I mean, is exist between matter and the planets or planetary system. Same thing is happening between the light. Only thing is when the as far as the Earth is concerned, the gravitational pull is very small. So you know, even the sun, it is the gravitational pull is so small that photons are not affected. Whereas black hole, as far as the black holes are concerned, the gravitational pull is so high that even the light experience the pull. Actually, that is all. That is the way it should be seen. You can read more about it. There are a lot of literature. It is one of the most like a lot of works have been done in this, so you can read more about it. And if you see something very interesting, you can share it with us also. Something more than this basic understanding. So it is otherwise so. There are a lot of
Okay, sir.
literature available. Yeah.
Sir, I have another question.
Yeah.
Like the regarding the color of the objects.
Hmm.
Sir, what is actually the color?
Color is something. See, actually, color is something which when the particular kind of photons reaches our retina, they gives a response, and that appears as some particular color. Because of course, there are color means different wavelength. You have photons of different wavelength, different have different attributes. Actually, one is the color. Actually, that is where we see it. Actually, because it strikes
Sir,
our retina and gives a particular. There are color receptors on retina, so that
sir, but
yeah.
actual question is,
Hmm.
like the bulb is emitting white light,
Hmm.
but when it fall on a black object, we see a black. When it
Hmm.
fall on a blue object, we see
Yeah,
the
blue.
light is blue.
Yeah.
So means the atom of that object is absorbing the white light and emitting only the blue light.
Yeah, reflecting. It is not absorption, it is reflecting. So there is a difference.
But
See,
if it is reflecting,
yeah.
then it should reflect the white light, but
No,
it
no,
is
it is
reflecting the
that
blue
is the
light.
property of the material that it absorbs all other colors and reflect back the blue color. That's all. Green means same. Green it will be reflected. It is not emitting. So there is a difference between emission and reflection. See, white is a mixture of all the colors. So when we say, when we are reflecting back the whole color, you will see white. If it doesn't reflect any of those colors, it is black. So if you reflect back one particular color out of the white, then that particular color it will appear as if it is having that color.
So what if a object is like of blue color,
Hmm.
and instead of white, I
You can
emit a
try that.
light?
Yeah, that's very interesting. You can try that. What do you feel? What will happen?
I never tried. So
Yeah, you try. I think it will be dark because that material can only reflect back that particular its color only. So it should appear as dark. You can try that anyway. This is
okay,
and
sir.
the theory is also available. I mean, you can try both theoretically and practically. You can see it's not very difficult because it should appear as black as far as I think.
Okay,
Anybody
sir.
else has any answer to that? Anybody tried that?
Sir, is there an example
Which one?
regarding this phenomena?
No, no, you can see that. You can see it yourself. See, for example, when you are going to especially when you are going to buy a dress. See, if you go in the night, there are all sort of in the showroom, all kinds of different colors can be there. Like so that is why very often we were doing the during the shopping, especially clothes. In the showroom, it appears very nice. When you bring it home, it doesn't look that nice. So it's a manipulation of the uh, coloring there. Actually, the lighting system there. So these things are possible. Okay.
Yes, sir.
Yeah, so I mean, this you can try after the lecture. You can go and try this, and tomorrow you can share your experimental result with us. And then the theory is also available. You can go back these things. I have also studied long time back. I just offhand I said I'm not claiming that I'm 100% right in this. So you can check what I said is right. So if I'm wrong, you can correct me tomorrow. Yeah, or the next whenever we meet next time. Yeah,
Okay, sir.
yeah. So anything else regarding what we have discussed?
No, sir.
So this now we see some of the first we'll try to see the energy bands of semiconductors of our interest. So generally we talk of silicon, then germanium and then the other kind of semiconductor which is of interest is a compound semiconductor, that is the gallium arsenide. So we'll try to see the actual energy band diagram of the germanium, silicon, and gallium arsenide, just to see the difference between them. So this is actual diagram of The left hand side is again is visible to all of you.
Yes, sir.
Yeah.
Yes, sir.
Yes.
So energy band diagrams are normally known as EK diagrams. So K, we have seen that K is the wave vector, or K decides the momentum. So energy band diagrams are essentially energy versus momentum, because H cut K will give you momentum. So it is essentially a graph between energy of the electrons and the momentum of the electron. So they are EK diagrams. So that is why sometimes they are known as EK diagrams also. Or K is the wave vector, that is 1 by lambda and things like that. Now, the second thing is you can see there is different orientation. Actually, you'll see one or two mix up there. That is because different directions are also there in the different directions in the crystalline plane. We'll come to that here. Actually, they are showing the crystalline, the energy band structure for two orientation, 111. I'll be discussing little later about this, and 100. Anyway, you are familiar with that, but still, so that is why you are seeing two kinds of this thing, the energy band structures. So you can see that there is a it's not like the way we have seen, like two bands we have mentioned. So normally when we draw the energy band diagram, so you may ask, then what I have shown earlier, that what we have seen is corresponding to lower end of the conduction band and upper end of the valence band. So that is what we have shown in earlier discussions for simplicity. The actual one is like this. Actually, the EK diagram will look like this, even much better. This is a two-dimensional view. One can take the three-dimensional view also. It's much more complicated than this, but simplest to the reality is somewhat like this. Actually, it's so you see that there are at least one or two conduction band minima. Then there are one or two valence band minima, etc. So now, similarly for germanium and silicon, and when you look into the gallium arsenide, slight difference you can see. You keenly watch, then you will see that difference. Now, coming to band gap. Band gap was mentioned as the conduction, the energy gap between the conduction band minima and the valence band maxima. So all the whatever be, so you have that is the that is, in fact, that is the first band gap, because if you look carefully, you will see there are various minima. It's not the only minima and maximas. There are other minimas and maximas are also there. But this is, so when we talk of the at higher energies also, you see some minimas, etc. But that forget about that. But generally we talk of the first band gap, that is the conduction band minima and the valence band maxima, the energy difference. So you see that in the case of, so along x-axis you have K and y-axis is the energy. So for the germanium and silicon, you see that it happens at different values of K. So so EG, you can see that it is mentioned there. The conduction band minima and valence band maxima in the case of germanium and silicon, it is at different values of K. Whereas in the case of gallium arsenide, you see that both lies at the same value of K. So depending upon this, you have two kinds of semiconductors. One is a direct band gap semiconductor, like gallium arsenide is a classic example of that, whereas germanium and silicon, it is an indirect band gap semiconductor. So this is very important. As we go further, this will be because so why I am spending so much time on energy band, because this is one of the most fundamental property of the semiconductor materials, and almost all properties of, especially the electrical properties of the semiconductor, depends on the energy band structure of the material actually. So we can go back, we revisit the energy band to understand any of the properties, any of the electrical properties of the material. So that is why, again, so similarly, when we say direct and indirect, it will have direct implication on their electrical properties. that we will be seeing later. So right now we need to understand that this is one is indirect silicon germanium are indirect band gap semiconductors, and gallium arsenide is a direct band gap semiconductor. One thing more, we will shortly we will be revisiting the mass of the electrons in this. So we will be seeing that towards the end of our discussion today. We will be seeing that the curvature of the CK diagram, that is the slope, the of this, the curvature of this EK diagram will decide the mass. So that means the mass will be varying at different, because it's a curve, so it will not be, it's not a straight line. So at different points you will have different masses. And again, another interesting thing, you will see that especially this is true for gallium arsenide. So you are seeing various valleys, etc. You will be studying, you have a paper on microwaves this semester, no? You will
Yes,
be
sir.
studying microwave this semester.
Yes, sir.
So have you heard of gun effect, gun diode, gun effect, etc.?
Not yet, sir.
Yeah, you will be studying. So there you will be seeing, again you will be going through the gallium arsenide band gap, band structure actually. So the interesting thing here is, when we go from one valley to other, lower valley to upper valley, the mass is if the mass decreases, that will have certain consequences. So you will see that that effect is used in certain microwave devices, and that effect is known as gun effect. GUNN. This is not gun. This gun. GUNN. It's the name of the person. So you'll be probably Dr. Vora will be teaching you about that. So you should remember that again. So all these things are very important. Like from the band structure of the material, you can find out those things actually. So right now, just remember that silicon, germanium are direct band gap. Sorry, indirect band gap semiconductors, and gallium arsenide is a direct band gap semiconductor. And then another thing we can see in the diagram is there are other, even in germanium and silicon, there are direct band gap at higher energies. So, but then the lowest is one is an indirect. So that should be kept in mind. And similarly, gallium phosphide, again, very widely used for making cheap LEDs, like the LEDs you see, yellow, red, and green. They are mostly made of gallium phosphide. Gallium phosphide is an indirect band gap semiconductor. So there, again, you will be studying about them in your optoelectronics paper, because those paper, I know that these papers are together. So there you will be studying. So gallium phosphide is an example of an indirect band gap, like silicon and germanium, but they are used for making LEDs very extensively. So you can, when you study the optoelectronics, you can go through the details about that, how the LED action takes place. So this is that way you have these two kinds of material. One is direct band gap like gallium arsenide. Then you have indirect band gap like germanium, silicon, gallium phosphide, etc. Yeah, that is one thing. Yeah. So I'm just showing the energy gap. Here you can see that silicon, I have shown the indirect band gap that is at a higher value. Otherwise, 1.1 is the gap. And whereas you can see that gallium arsenide, it is again very close to silicon, 1.43 electron volt. This is at room temperature actually. So corresponding to wavelength of 1100 nanometers. Gallium arsenide, it is 873 nanometers, and aluminum arsenide, it is 556 nanometers. So then this, you will see that these materials, gallium arsenide like materials, are quite popular for making LEDs, and whereas silicon is not used for making LEDs because of the these restrictions, because they are being indirect band gap material. Otherwise, the wavelength band gap is very close, so it could be used for making IR LEDs, but it is not used. Because there are restrictions on the transition in the indirect band gap semiconductor, because you have in physics, for any transition to take place, your momentum and energy has to be conserved together. So in the case of a direct band gap semiconductor, since it occurs at the same k value, so both energy and momentum can be easily conserved. Whereas in the case of silicon-like material, indirect band gap material, the momentum conservation is tricky because the photons cannot take that much momentum. So that way there will be uh, violation. So it is cannot be a two particle interaction. When we are talking about the transition, actually an electron is making a transition from valence band to conduction band, or conduction band to valence band. Absorption means a photon is getting absorbed. That means electron will be going from valence band to conduction band. Emission means an electron will be coming, making a transition to the uh, valence band, recombine with the hole, and then they will emit the that band gap energy. That is a direct transition. But in the case of indirect band gap, there are other three particle transitions are involved. Somebody has to take away the momentum. So there will be, very often we talk of non-radiative transitions in the case of silicon-like material. And in the case of gallium arsenide, we talk of radiative transition. That means photon emission will be there. In the non-radiative means no photons are emitted. Mostly it will be absorbed by the surroundings. So that is why they are known as non-radiative. So radiative transitions are generally efficient in the case of direct band gap semiconductors. They are very often used for uh, making LEDs. Whereas this silicon, especially silicon, is quite popular with the making photodiode for detection. So you'll see that. So this, I will not be going into those details because you will be studying it in your other paper on optoelectronics, where you will be seeing what are the conditions for making photodiodes and what are the conditions for LEDs and all those things. So let us not spend time on that, which you will be studying. Yeah. Now, another important property is isotropy and anisotropic properties. See, very important for this crystalline material is the crystalline planes. Actually, there are different crystalline X, Y, Z axis. There are many various planes one can talk of when you take a three-dimensional picture. So very often we talk of the crystalline planes, and the question arises whether their properties are same in all the planes. If the properties which we are talking of are same, then we say it is an isotropic. And if it is different in different orientations or different direction, orientation means different directions basically. So then we say it is anisotropic. Most of the crystalline materials are anisotropic that way. So what is the meaning of iso? Iso?
Same.
Similar.
Similar or same. Actually, like isobar. What is isobar?
Same mass.
Same mass number but different atomic number.
Isobar. Isobar.
Pressure.
Yeah, bar means it is pressure. Isobar means equal pressure. Geography.
Okay.
Isotherm,
Heat.
Same temperature.
same temperature. Isosceles triangle.
Same
Same side.
two same side.
Same side.
Yeah, that is there. It is slightly different. It's two sides only. Otherwise, all the three sides are equal. Then we say equilateral triangle. Actually, so it is isosceles means two sides actually. So anyway, so isotropic and anisotropic. So again, the problem with most of this crystalline material is they are highly anisotropic. That means the parameters which we are talking of, we are going to introduce certain parameters. All those parameters will be different in different directions. So that way, they are highly anisotropic. So that we should keep it in mind. So now, let us, so we said we need to consider the properties or some parameters. So what are the kind of properties we consider for a material? Normally we consider electrical, mechanical, chemical, and now question arises why we need to consider the other properties. Okay, electrical I can understand. Why we need to consider mechanical and chemical? So first of all, let us discuss what are the electrical parameters of the material we will be considering. Yeah.
Current, voltage.
Conductivity.
Parameter of the material, actually. Parameters, not the current word. That is external. And we are talking, see, we are focusing our first part of our discussion is on the materials only. So the material properties. When I am talking about the properties means electrical properties or the properties of the material. Material like silicon, for example. We are not talking beyond like external. So which is inherent property of the material. So what are the inherent electrical properties of the material we need to consider?
Conductivity.
We have seen that conductivity, but conductivity depends on the carrier concentration and the mobility. So when we talk of the electrical characteristics, we talk of the carrier concentration for at a particular temperature, because as he has rightly pointed out, one of the most important electrical parameter of the material is the conductivity. But conductivity is in turn depends on the carrier concentration and mobility. So we talk of carrier concentration as the one of the parameters. Second is the mobility. Any other parameters? Because since we have not discussed, but you are familiar with any other parameters of interest, electrical parameters? Yeah. Any other parameters, electrical, which decides the electrical properties of the material? Any idea? Hello? Hello? Hello?
Yes, sir. Yes, sir.
Actually, I don't know whether the connection is low, like the last time it happened also, no. So if you say something in between, then only I know you are there. Otherwise, I don't know whether you people are there also. Yeah, so what is the other electrical parameters we need to consider for the material? See, we will see later on that there is another kind of current which flows, that is the diffusion current. So diffusion constant of the material also is very important. So these are some of the parameters we need to consider. And again, all these parameters are decided by especially the mobility, diffusion constant, etc., are decided by the mass of the electrons. So these are the parameters we need to consider when we talk of the electrical parameter. Okay. Now, what about the mechanical? What do you mean by mechanical parameters? Can you give me an example of a mechanical parameter? Yes.
Temperature variant, sir.
When we talk of the mechanical properties.
Sir,
Sir,
shearing strength.
Yeah, it
Sir,
is
how
about the
much stress
stress.
it can
Yeah.
intake?
Pardon?
How much stress it can intake?
Yeah, that is what it is about. You have the elasticity, shear stress,
Apply
and
pressure.
like
Uh,
elastic constant. And why do you think it is important for us for knowing the mechanical properties? Okay, why
Yes,
I am
sir. It is.
discussing? Yeah.
So because when we will be processing it, we will take it to means a lot of just like grinding of
Yeah.
the.
Yeah, that
As,
is it is relevant, but mostly we'll see that we are using MEMS devices actually. There, the elasticity, and all those things become very important. So otherwise, what you said is also true. When you are processing it, whether it is brittle, whether whether it can go through all those mechanical pressures, stress, and any additional stress it is creating, that also matters. But mainly, the mechanical properties are considered from the point of view of MEMS actually, because you want to use silicon as this material for because you want to take advantage of your silicon fabrication technology for making MEMS also. That means the mechanical devices also you want to make with silicon as far as possible. So that means the mechanical properties of the silicon should be found, and we have to streamline it. So we need to consider those elastic and other mechanical properties. And what about chemical properties? Yeah, why we are interested in the chemical properties? Are we interested, or we need not be worried about the chemical properties?
No, sir. While processing, we
Tooling
means a
manufacturing.
lot of chemical are used, so
Yeah,
chemical properties are important for that
yeah.
purpose.
So how the process will what is the role of chemistry in processing actually, or the chemical properties? Can you give me an example?
Sir,
Like
in
if we have
etching,
to,
Yeah,
sorry.
that is very rightly said. Actually, you will see that those who have done, especially MEMS, they know that the etching rate is different in different directions. Actually, so the etching rate. So and then again
Reactivity.
yeah. Anything else? Yeah,
Reactivity, sir.
pardon?
Reactivity.
Yeah, reactive. Actually, the etching rate is actually, in a way, one can talk of reactivity or etching rate is similar actually. So, broadly, we can say the reaction rate or the etching rate. Very often, that is important. Then, the kind of atomic density in different direction will decide the interaction. For example, you might have studied that. That was a problem with the development of MOS technology actually. uh, Traditionally, one kind of orientation was quite popular with bipolar, but if they tried to use the same uh, orientation with the MOS, it was very difficult to get proper repeatable MOS structures. So then the chemistry has to change because some of the chemicals used, especially the sodium hydroxide, etc., based chemical processing was giving trouble. So then later on, of course, the different types of most technology use a different kind. So we'll be coming to that a little later. So I'm just not jumping the gun right now. So the chemistry play a very important role even right from the beginning. So that chemical properties are also to be known. And then again, another important thing is which direction we will be later on. We will be talking of surface states. Uh, you have any idea about what is the meaning of surface states? Heard of surface states? Hello.
No, sir.
See, actually, whatever we have said so far, at the very beginning, I said it is for a material whose dimensions are going in all the direction to infinity. But it is never like that. You have a discontinue at the surface. You are coming to surface actually. What happens at the surface?
sir, silicon has means like silicon has 4 bonds, so one of the bond is not there.
Yeah. So that is known as dangling bonds. Dangling means hanging. It is just hanging. There is nothing, no neighbor. So they are known as dangling bonds, and the dangling bonds are chemically quite active. So from the atmosphere, normally they take up oxygen and form silicon. That native oxide is formed because of that only. So otherwise, they will form what is known as physics point of view. They are known as surface states. So that the surface is a uh, main issue in the, especially device dimensions are very small, and the MOS devices you are using, the device conduction is at the surface only, near surface only. So there, the surface states play a very important role, and you have to reduce the surface states. That is why we very often use silicon dioxide as a passivation layer. Passivation means you are pacifying it. You are cooling. I mean, and surface is quite active. You want to, like Hindi, we say, shant karna. So passivation means like you are trying to cool it, not cooling in that sense. You are not reducing the temperature, but the chemical activity is reduced. So like as a small child is quite hyperactive, so you just give them some toys or something to make them calm. So that is the meaning of passivation. So silicon dioxide is used as a passivating layer. So surface states play a very important role, and again in different directions the surface states are different. Actually, that was another reason why bipolar technology is a bulk device. So there the surface states may not be very critical, whereas MOS being a surface device, the conduction is very close to the surface states are very important, so you need to control the surface states. So what I want to say is, when we talk of the properties, the anisotropic properties, so we need to consider this aspect also, that electrical, mechanical and chemical properties in different directions are different. So then so that need to be understood. So the which direction we are talking, when we are defining a parameter, we need to know which direction or which orientation we are talking of. So that's a very important thing. Yeah. So this is what we are talking of, or that different crystalline planes actually. So they are very often known as identified using Miller indices. It's coming from the crystallography. So this is the three quite popular orientations. There are other orientations also. One can see that other orientations are also possible, but this first and the last one is the most popular one. 100 is predominantly used for most technology, and the triple one orientation is used for bipolar technology. These are the two one. There are for as far as MEMS are concerned, there are other orientations are also used actually. So these are the basic crystal orientations given by, and that normally denoted by the Miller indices. So these two orientations are the most popularly used orientations. Yeah. So when you take the silicon wafer, this you might have studied. Have you studied this earlier, like primary and secondary flats, and how to identify the wafers and all those things? N type, P type, and orientation. So we are given a wafer, how to identify whether it is from the physical observation, or just seeing it, you can make out which is N type and which is the orientation. Have you studied this earlier?
No, sir.
Yeah, I thought that you might have studied it in your IC processing paper, but anyway, this is quite useful. So there are two when you are talking about the wafer, you have two flats. You can see that one is primary flat, and this is the one is a small one, that is a secondary flat. And depending upon the position of the primary and secondary, one can identify different orientations, different doping type, etc., whether it is N type and P type, etc. So this is when you are working in the lab, these kind of things are important. So this is for the general information. I just posted it here. So this is another way of seeing it. Let's see, the top one is the silicon ingot. So you have the silicon ingot. Through the Czochralski technique, you grow the silicon and then you make wafers out of this, cut it. You can see here you have wafers, and the wafer, then you, depending upon the orientations, you have this primary and secondary flats are made so that you can easily identify it in the lab. So that is the thing. So this, anyway, we have already mentioned that the properties and carriers of silicon is, one is the mobility, then the velocity, then then other one parameter is the charge. Of course, we have not mentioned about the electronic charge, then the band gap, then mass of electrons, then diffusivity or diffusion constant. These are some of the properties of the carriers, and most of these parameters, for example, mobility, diffusivity, etc., will be dependent on what?
Temperature.
No, temperature, of course. Temperature is external parameter. We are not talking internal parameter. In this interdependence of which parameter? Charge, does it depend on any other parameters? Electronic charge.
Carriers. Number of
No,
carriers.
no, there is one charge, the unit property of one electron does not depend on the other. So their charge is fixed. Velocity, of course, depends on the temperature. So velocity will be decided by the mobility, and mobility is dependent on what?
Concentration of important concentrations including acceptor and donor lines.
No, mobility doesn't depend on that. Mobility is
Sir,
mobility will
rate
be
of
decided. See, for example, I don't know who is heavier in you among you. Let us say Bhaskar is the heavier man, and I think I don't know who is the thinnest. Nithi is the thinnest.
Nikhil.
So whose mobility will be more? Whose mobility
Nidhi.
you will? Eh?
Nidhi
The
ki
lighter
mobility.
Yeah.
one.
So the mass will decide this. So mass of these carriers are very important as far as the diffusivity, mobility, etc. Mobility in turn will decide the velocity, actually. So we look into the mass of electrons. Now the question comes: why we need to consider the electron mass is known, like from the time of J.J. Thomson, we know the mass of the electrons. Why we need to consider mass of the electron? Yeah, any idea? Why we? Because mass of electron is well known, because we have already said carriers are electrons, whether it is holes or electrons, they are electrons. So and mass is well known. You have all those famous E by M ratios and experiments. Then electron charge is known, then E by M is known, so you can find out the electron mass. Then why we spend time on the mass of electrons here? Yeah,
Because there is a effective mass which is
yeah,
considered.
actually there is a problem. So electrons are not moving in vacuum. Electrons are moving in a medium, or in the inside the material. Actually, we have seen that there is a periodic potential. There are other things also affecting, influencing the uh, movement of the electrons. So we need to bring in the concept of effective mass. That is why I want to bring in the concept of. See, actually, this is a very interesting parameter is introduced, which is known as the effective mass. It's a very interesting concept. So this is helping. And then that time I didn't want to mention this, but in the different orientation, this effective mass is going to be different. We'll see why it is different. So the nature of motion of the carriers, one thing we can immediately understand is nature of motion of carriers within the material is going to be different. Why it is different? Why it is going to be different? Hello? Why it is going to be different? Okay, we know that it is moving and it will be different. So what difference will be there? Yeah. What difference will be there?
The medium.
Yeah, medium, how it will influence the motion, actually. So that is what we are, let us see that. So actually what happens is there is, see, the electron is moving. See, for example, you are applying an external electric field. Newton's law says that uh, force, when you have force is applied, acceleration will be there, and acceleration will be proportional to the force applied. But there will be internal core atoms and ions are there. They can influence the motion of the carriers. So the net force is what is acting. So even if you apply a large force, the acceleration, and you know the mass of the electron, you may not get that kind of acceleration. So because there are additional force, internal forces acting on it. So in order to take into account that additional forces acting on those carriers, you have introduced a concept what is known as the effective mass. That is, the carriers are moving inside the material with a different mass. It's not the rest mass or the mass of electrons outside the material. It is different because even though they are the same, but then here it is as if they are moving with a different mass. So that is, so it will take care of the internal forces. So you need not worry. So it is, you define a mass, so which will take, or we define an effective mass actually. So that is the concept of effective mass actually. So the important thing is electrons is not accelerated to the external force alone, but rather is a combination of this. So you can define the acceleration in terms of the uh, by m star actually. So that is, so very often it is denote the star mass of the carriers within the material is shown to be m star. So we can use the classical picture so long as you consider that you can introduce the concept of effective mass. Then one thing we need to keep it in mind, different directions, the nature of forces are different. So the internal forces are different. So the effective mass will be different in different direction. So highly anisotropic mass will be anisotropic. Then mass of electrons in different materials. For example, if you take silicon or germanium, the effective mass of electrons will be different. In silicon, it will have a definite value. In germanium, it will have a different value. Then, if you consider hole, even though we know that hole is nothing but electron motion, it will have a different. What do you expect? Which will have more electrons or holes? Which will have more mass? Effective mass. Both are electron motion. So what will have more, or they will be same? Effective mass of electrons and holes in different materials? Yeah.
Mass of hole would be greater, sir.
Mass of?
Holes would be greater.
Yeah. So actually, we will see that in any material, mass of holes will be higher because they are moving, the internal forces are moving, they are moving from one bound state to another bound state. So the internal forces are more on them. So naturally, it will be, the mass will be more. So you will see that the mass will be more. So that is another important thing, that the effective mass is different for different materials. For electrons and holes, they are different, and different directions, they are different. So this derivation actually I picked up from another slide. So you can just see, it is visible.
Yes, sir.
Yeah. So actually, what we are doing is we are trying to find out the, in terms of EK diagram, energy and momentum. We want to find out the relationship for the m star. So these are all known. So what we have done is energy is written in terms of the momentum. Then momentum is replaced by hk. So that is a quantum picture. And then you take the when you differentiate it, you will get, and then you see that the last one, that is m star, because the slides will be available, you can go through it a little later. But m star is h cut squared divided by the d by dk squared, this the second differential of d by d. So I mean, now I want you to look back to the energy band structure. At each point, the effective mass is going to be different because it is going to be decided by the curvature of the energy band, EK diagram. So that is the most important thing. So it can be positive depending upon the curvature. It can be positive, it can be negative, it can be higher than the rest mass of electron, it can be more than or less than. So all those things are possible, provided we accept that this m star is decided by the curvature of the EK diagram. So this is the most important thing which we need to keep in mind. The effective mass will be dependent on the curvature of the energy band, and the mass decides most of the properties of the material, whether it is the mobility, which is one of the most fundamental parameter, or the diffusion constant. So that way, the effective mass play a very important role in deciding the electrical properties of the carriers or the material. So different materials will have different effective mass. So that's what I said. It can be negative, it can be positive, it can be more. So now I think I'll stop it here. So now we have a few questions. Or we will, or so if you are able to answer it now, it is okay. Otherwise, you can go back and think about them. So, shall I go to the questions? Hello. Yeah.
Sir, you can ask these questions on the next lecture before starting. Then we could remind what we have read in the previous